Welcome to Module 6. In this module, we will talk about regression. This module covers Chapter 9 from your textbook. Regression is very useful statistical procedure. If you read journal articles published in nutrition and like family consumer sciences and other fields, you will see regression analysis too often compared to other statistical methods. So it is very useful and you will see we can like answer many different research questions using regression analysis. So in this module, we will talk about the background of linear model and a regression, assumptions for regression analysis, and how can we address the fit of the model, how to interpret the model parameters, and we will use SPSS at the end. We will see how to use SPSS to run regression analysis. There are some similarities between regression and correlation, but there is a like significant difference between these two statistical analysis. So in correlation, we are examining the relationship and correlation and association between two variables, between two continuous variables, for example. But in regression, we are trying to predict one variable from another variable. In regression, we are also examining kind of relationship and association between two variables, but the main focus here is on prediction. So regression in general predicts a line, and the strength of the line is what indicates predictability. So as I said, it is very common statistical procedure. Regression analysis is very common. It's very useful, and it's the especially for prediction. For prediction, we use regression analysis. But here, remember, we have different types of regression analysis. But when we say regression analysis, it is referred to as a simple or multiple linear regression analysis. But there are other types of regression analysis, which is not the scope of this module. So we will not cover other types of regression analysis. We will cover simple and multiple linear regression in this module. So as I said, the purpose and the goal is to predict and explain value of one variable from another variable. So for example, we need to know which patients will get cancer. So we are predicting here. We are predicting which patients will get cancer or what risk factors predict a specific disease. Here we are predicting. So prediction is the core of regression analysis. We need to know which students will drop out, which ones will succeed. These are other examples. So in order to answer these research questions, we need to run a regression analysis. So regression analysis, it's based on predictive statistics. And when we say prediction, just like other statistical procedures, we have two main different types of variables when we are trying to predict one variable from another variable. So we have independent variable or multiple independent variables and just one dependent variable. So independent variables are also called predictors. So in regression, we can have one independent variable or one predictor and one dependent variable or outcome variable. So we are trying to predict the outcome variable or dependent variable from independent variables or predictor variables. So as I said, in this module, we will learn about simple linear regression or multiple linear regression. In simple linear regression, we have only one independent variable and one dependent variable, or one predictor and one outcome. But but in multiple linear regression, we have more than one predictors and just one outcome variable. And the goal and the purpose here is to kind of determine and assess how accurately can the outcome variable be predicted based on the value or values of one or more predictors. This is regression analysis. As I said, there are different types of regression analysis. We have logistic regression. We have, we can use odds ratios. Uh, we have different types of regression analysis, but these are not the scope of this class. We have uh, like bootstrap regression analysis. We have multiple logistic regression. We have Bayesian regression. So there are different types of regression analysis. So regression analysis does not analyze interventional research. We are just predicting outcome variable from predictor or predictors. So simple linear regression is a means to estimate the value of a dependent variable or outcome variable based on the value of an independent variable or predictor variable. So here it is simple linear regression. So we have only one independent variable. Dependent variable is the variable the researcher is trying to predict. An independent variable or predictor variable is the variable the researcher uses to predict the dependent variable. In multiple linear regression, which is an extension of simple linear regression, and it contains more than one predictor variable. So we enter all those independent variables or predictors into the analysis, and that's called multiple linear regression. There are some YouTube videos, so I would like you to just click on them and watch them. These are very useful videos. Whenever we talk about regression analysis, it is a line. So that's why it's called linear regression. So it is a line, and we have two axes here, y-axis and x-axis. So x is predictor variable or independent variable, and y-axis represents dependent variable or outcome variable. And the line is our regression line. So what is the linear model? Linear model is a way of predicting the value of one variable from another. That's a linear model. And it is a hypothetical model of the relationship between two variables. So this is a linear one, so it is just a line, and it represents both, y-axis and x-axis. So the linear model is a equation of a straight line. And this is the equation for a straight line. I assume we all learn about these equations in high school. So it is very simple equations. And this equation represents a line. And we can draw this equation on y-axis and x-axis, and it will become a line. So this equation has different parameters, and we need to know these parameters. So we have y, which is our outcome variable. We have b0. B0 is the intercept, the value of y when x is 0. That's b0. And we have beta. Beta is the slope of the line, or the gradient of the line. We have x here. X is our independent variable, or our predictor variable. And we have error term. So that's the equation of a straight line. So here, as we can see from the figure, so we have beta, or slope, and we have intercept. So this intercept is the where the line kind of hit the y-axis, and that intercept is b0 in the equation. In our equation, it's b0. That's our intercept. It's the point at which the regression line crosses the y-axis. So this equation is a simple linear regression model. So whenever we are trying to, you know, show our regression line or regression equation, if it is a simple linear regression, that would be our equation for simple linear regression. If we have a multiple linear regression, we will have just one outcome variable. We will have just one b0, but we will have multiple betas and x's in this equation, and we will have error term for each independent variable. So this is an example from your textbook. So this is an example. Let's see. We have 200 different album releases. So our sample size, or n, is 200 in this example. And the research question is, uh, you know, a record company boss was interested in predicting album sales from advertising. So the researcher tries to predict. So we will use regression analysis to answer this research question. The sample size is 200 different album releases. The outcome variable is sales. And the predictor variables are the amount in pounds spent promoting the album before release, number of plays on the radio, and image of the band. So, can you tell me what type of regression analysis this is gonna be? So, we have one outcome variable and three predictor variables. So, this is gonna be a multiple linear regression, because we have, you know, three predictors, not just one predictor. Before running the regression analysis, just like what we have to do with correlation analysis or other statistical analysis, we need to test for some assumptions. Before running the regression analysis, it is better to kind of draw a scatter plot showing the relationship between the outcome variable and predictor variable to see if there is any line here, if we can see a slope in the line. If we see a slope, if it is not just horizontal line, we can assume that there is a relationship, there is a correlation between these two variables. Then we can move on to run the regression analysis. If this red line was just straight and horizontal line, we would assume that there is no relationship between, y and x, our outcome and predictor variable. Then there is a no, there is no need to run regression analysis here. This is the scatter plot for a simple linear regression because we have just one outcome variable and one predictor variable. If we want to like kind of make a scatter plot for multiple linear regression, we can also do that. But that can make a complex figure. And if we have, like, let's say, 5 or 6 predictor variables, the the scatter plot will be very complex to interpret. So it is better to run scatter plot, one by one. So we need to make a scatter plot for predictor one and outcome, and then predictor two and outcome, and predictor three and outcome. But if we have only, like, let's say, two predictor variables and one um, outcome variable, then it will make a 3D scatter plot figure, which we see here. And again, based on this, I can say that there is a there's a relationship between album sales, which is our outcome variable, advertising budget, and radio play, which are my predictor variables. So I can also draw a scatter plot with several predictors. So this is the equation. This is our equation when we have more than one predictor variable. So we have one outcome variable, y, and b0, which is our constant, or intercept. This is the point at which the regression line crosses the y-axis, and we will have multiple betas and x's. So betas are the slopes for each line in the regression model, and the x's are our predictor variables, and we have a total error term here, which is epsilon. So this is the model for our multiple regression. So as I said, B0 is the intercept. This is the value of y variable when all x's are 0. So if we have multiple linear regression, B0 is the intercept, is the constant, is the value of the outcome variable when all x's are 0. If we have a simple linear regression, then B0 is the intercept at which the point at which the regression line crosses the y-axis, or it is the where our predictor variable, just one predictor variable, or x equals 0. That's B0. So beta values are the slopes or gradient or coefficient. So when we interpret the regression model or the regression output, we will see coefficients. Those coefficients are the slope. So in multiple linear regression, we have multiple predictor variables. So we have variable 1, variable 2, variable 3, and n variable. So we will have beta 1, beta 2, and beta n, which are indicating our coefficients or slope of the line in our equation. We can determine and assess the overall model fit. So the model we get from plotting our outcome variable and predictor variables. That model is based on the data we have. And that model might not reflect reality or the general population. So that's why we need to kind of assess the model and assess how well the model fits the observed data. How can we do that? We have two ways to do that. We have F statistic and we have R squared. R squared and F statistic can indicate how well our model fits the observed data or how well our model reflects the reality or general population. In order to determine F statistic and R square, we will need to know sums of squares. There are three main types of sums of squares. So sums of squares can be total, like total sums of square, or sum of squares for residuals or errors, and sum of squares of the model. So sum of squares of total or total sum of square is the difference between the observed data and the mean value of outcome variable. The sum of squares of the residuals is the difference between the observed data and the model. And the sum of square of the model is the difference between the mean value of the outcome variable and the model. So we have three types of sum of squares. Sum of squares total indicate total variability or variability between scores and the mean of the outcome variable. Sum of squares for residuals or error variability is the variability between the model and the actual data. And the sum of squares for model is the model variability, the difference in variability between the model and the mean value of the outcome variable. After calculating this, we don't need to calculate this by hand. So SPSS or other statistical software will do that for us. But these are like kind of a background of what is going on behind the scene when we are using SPSS. R and R squared. R is the remember from correlation analysis. That's the same R. It shows the correlation. R squared is the proportion of a variance accounted for by the regression model or the amount of variance in the data that is explained by the equation. So remember the definition of R squared, it's it is related to proportion. But when we trying to report R squared, we will report it in percentages and we will see that. And we have adjusted R squared. This is an estimate of R squared in the population. And the F statistic, this is another way of measuring of how much the model or how well the model represents the reality or the general population. Whenever our model is good, then the means of square for model will be large and the means of square for the residuals will be small. So this is the formula for F statistic. This is another way of testing of the fit of the model. And it uses mean squared uh, for model and mean squared for error or residuals. Remember, when we say residuals or errors, these are the same terms, so we can use them interchangeably. We will get F statistic in a ANOVA table. So whenever we run regression analysis, SPSS will provide different and several tables. One of them is ANOVA table. And in ANOVA table, we will see F statistic. And this is the formula for F statistics. Again, you don't need to remember or memorize these formulas, but this is what SPSS does behind the scene. So the F test or F statistic looks at whether the variance explained by the model is significantly greater than the error within the model. It tells us whether using the regression model is significantly better at predicting values of the outcome than just solely focusing on the mean of the outcome variable. And this is the formula for R squared. Again, this is another way to test for the fit of the model. R squared is the Pearson correlation coefficient squared. This is the same, topic. This is the same concept here. In regression analysis, as I said, SPSS provides several tables when we are running regression analysis. One of them is T statistics. So SPSS provides T statistic for each individual predictor. And this is the formula for that. You don't need to remember that, but this is a T statistic formula. How to get T statistic for each individual predictor in the regression model. So let's say based on F statistic and R squared, our regression model look good overall. But we have some problems because of outliers or influential cases in our data set. So in data set, we can have outliers or influential cases. And we need to determine that we need to diagnose uh, outliers and influential cases. And there are different ways to do that. So for uh, we will have residual statistics, which will show standardized residuals, and we have Cook's distance, and this Cook's distance will help us determine outliers and influential cases. This is a very important point. Outliers and influential cases are potential sources of bias in a linear model. Regarding standardized residuals, so we can determine outliers by looking at standardized residuals. In an average sample, 95% of standardized residuals should lie between plus minus 2 standard deviation. 99% of standardized residuals should lie between plus minus 2.5 standard deviation. In order to identify and diagnose outliers, so any case for which the absolute value of the standardized residual is 3 or more is likely to be an outlier. The Cook's distance, it measures the influence of a single case or single observation or a single row in our data set on the model as a whole. Absolute values of Cook's distance greater than 1 may be cause for concern. And here is an example. So we have case 30. So imagine we have a data set and our data set has different columns and different variables. Uh, One of the variable is study ID. So study ID number 30 is an influential case, is an outlier. So in this table, case number 30 included and case number 30 excluded. And this table kind of measures the difference between two conditions. One condition, case 30, is included in the model, and situation and condition number two, case 30 is excluded from the model. And we can see here by including or excluding case number 30, we see a yeah, kind of a change in the linear model. So this table kind of indicates the importance of diagnosing influential cases or outliers. As I said, we need to check for assumptions before running the regression analysis. And by checking the assumptions, whenever the assumptions are met, we can generalize our model to the entire population. These are the main assumptions in regression. Outcome variable must be a continuous variable. So outcome variable cannot be a dichotomous variable, cannot be a categorical variable. Predictors can be continuous or dichotomous. So dichotomous are like male, female, yes, no, ill, not ill, healthy, not healthy. These are all dichotomous variables. So predictors or independent variables can be continuous or dichotomous, but outcome or y or our dependent variable must be continuous. Predictors must not have zero variance. The relationship between outcome and predictor should be linear. We have to have independence, um, which means all values of the outcome should come from a different person. Remember, we can use categorical variables in our outcome variable if we have more than five categories. But it will be really hard to interpret. So it is better to have continuous variable for our outcome variable. I'm gonna skip this and I'm gonna show you how to, check for assumptions. So one of the main assumption is homoscedasticity and independent residuals. For homoscedasticity or independence of errors, we will plot and I will show you how to do that in SPSS. And we will have normal probability plot for normality of errors assumption. Multicollinearity. Multicollinearity, it's important in multiple linear regression. So in simple linear regression, we don't have to be worried about multicollinearity. So multicollinearity exists if predictors are highly correlated. So imagine, for example, let's say I would like to predict uh, total blood cholesterol levels based on BMI, body weight, and height. I will have multicollinearity problem here because my outcome variable is total cholesterol level. That's okay. That's fine. Um, we don't need to worry about that. But my predictor variables, BMI, height, and weight, these are highly correlated with each other. So I will have multicollinearity issues here. So I need to kind of test for multicollinearity in multiple linear regression. And in SPSS, there are two ways to do that. We have tolerance So in a table, SPSS will provide a tolerance table and VIF. So tolerance should be more than zero point 0.2 and VIF should be less than 10. Then I would say there is no there is no issue regarding multicollinearity, or the assumption for multicollinearity has met, has been met, something like that. So multiple linear regression assumptions are just similar to simple linear regression assumptions except for multicollinearity. So before running simple linear regression or multiple linear regression in SPSS, we need to check for linearity. So we will use scatter plot, and for simple linear regression, and for multiple linear regression, we will look at scatter plots of each predictor with the outcome variable. And we can also use partial regression plots if needed in order to check for linearity. We want to see to have a roughly straight line pattern when we are plotting, uh, the predictor and the outcome variable. The normality of residuals. This is another assumption in regression. So this one and the next a few slides are the same as prior slides, like regarding assumption testing, but these are in simple terms. And here I just want to show you how to kind of test for these assumptions. So for normality of residuals, we can histogram of standardized residuals. We can use p-plot, pp-plot. We can use qq-plot. We can use Shapiro-Wilk test on residuals, but most of the time we will use, a histogram and pp-plot when we are trying to test for the normality of residual assumptions. So this assumption is why we want to test for normality of residuals, because regression assumes that the residuals are approximately normally distributed. Remember, residuals are errors. So when we say errors are approximately normally distributed, that means we don't have any problem with errors or measurement error or whatever. So what we want to see here, the histogram should be roughly bell-shaped, and the points in PP plot should be close to the diagonal line. Homoscedasticity, this means the residual should have constant variance across predicted values. How can we check for homoscedasticity? We need to scatter plot of standardized residuals versus standardized predicted values. We want to see a random cloud of points. No funnel shape, no obvious pattern. In those cases, we can say the assumption for homoscedasticity has been met. Independence of errors. This means the residuals or errors should be independent from one another. How can we check for this assumption? We can use a Durbin-Watson statistic. And that's a box, and we need to check um, in SPSS when we are running regression analysis. What we want to see here, a value around 2. Roughly 1.5 to 2.5 is also acceptable. And multicollinearity, remember, this is a very important point. This is just for multiple linear regression, not simple regression. How can we check that? we can use tolerance test, VIF test, or optionally collinearity diagnostics. So tolerance more than zero point 0.1 or above zero point 0.2, it's preferable. VIF should be less than 5 and definitely below 10. For outliers and influential cases, there are different methods, but as I said, we have Cook's distance and we have standardized residuals. Standardized residuals usually within about -3 to +3 is acceptable. The Cook's distance should be less than 1 in those cases, and there are other tests for checking for outliers and influential cases. And in these cases, we can say the assumption for outliers and influential cases uh, are met. Logistic regression is another type of regression analysis, but this is totally different from simple linear and multiple linear regression. In in simple linear regression and in multiple linear regression, our outcome variable is a continuous variable, but in logistic regression, the outcome variable is categorical. And most of the time, it is just two levels. It has two levels. So it is dichotomous. For example, have a disease or don't have a disease. Uh, these are examples for logistic regression. And in logistic regression, instead of having beta or coefficients, beta coefficient, we have odds ratio. And sometimes it is hard to interpret the odds ratio. Um, since this is beyond the scope of this class, I just wanna skip this. But remember, odds ratio, it's around 1. So if odds ratio is equals to 1, then we say exposure does not affect odds of outcome. If odds ratio is above 1, we say exposure associated with higher odds of outcome. And if odds ratio is less than 1, we can say exposure associated with lower odds of outcome. When we are trying to run regression analysis in SPSS, there are different methods on how to enter the variables into the model. So one is hierarchical entry. So in this method, we have to have a known predictors based on past research. So we enter predictor variables one by one. And I will show you how to do that in SPSS. So we can do this, but we have to have a solid, kind of theory in order to use hierarchical entry. We have forced entry. Uh, Most of the time we use forced entry, which means all variables, all predictors are entered into the model simultaneously at the same time. We have stepwise entry. We have to have mathematical criteria, and computer selects variables based on mathematical criteria here. But just remember, most of the time we use forced entry. So here how we can use SPSS in regression. So this is the example from your textbook. Again, we have our sample size is 200. The outcome variable is sales in the week after release, and we have three predictors or independent variables. So first, running the before running regression analysis, we need to check for linearity and check for any unusual cases by scatter plot, by just, creating scatter plots. And then we have to check for other assumptions like homoscedasticity, independence of error, normality of residuals using different methods. And then we can check the fit of the model. We can check the beta coefficients and all those things. So I'm gonna skip these slides because we are gonna use SPSS. So this is one of the tables SPSS will provide when we are running regression analysis. And this table shows the model summary. It provides R square, and adjusted R square. This is the F statistic. As I said, there is in SPSS output, there will be a table titled ANOVA, and we can find F statistic in this table, which is here F, and we have p-value. So for our data set, in this example, F is 99.59, which is significant at p-value less than 0.001. Therefore, we can conclude that our regression model results in significantly better prediction of album sales than if we use the mean value of album sales. The regression model overall predicts album sales significantly well. And this ANOVA table also provides the sum of squares. So we have sum of squares for regression, sum of squares for residual, and sum of squares for total, which is SSM, SSR, and SST. And we have also mean square, MSM, MSR, and we can use this to calculate F statistic. But there is no need to do that because SPSS provides F statistic for us. And this is the model parameters or coefficients, and this is one of the main tables we will look at when we are doing a regression analysis. So we have constant value here. The constant is B0, or it is the intercept. And we have advertising budget. So this model is simple linear regression. Why? Because we have only one independent variable here, which is advertising budgets in thousands. And we have unstandardized beta, which is the beta coefficient in this model is 0.096. That's the slope, that's the gradient, or our beta coefficient, or beta 1. We have standard error for that coefficient. We have t statistic and p-value, which is it is significance. So this table provides estimates of the beta values and the significance of these values. B0 or constant is the y-intercept, and this value is the value B in the SPSS output for the constant. So from the table, we can say that B0 is 134.14. And this can be interpreted as meaning that when no money is spent on advertising, which means when X variable, when a predictor variable, when advertising budget is zero, the sales is gonna be 134.14 albums. So we can plug in those values into this equation and we will get this equation at the bottom. And when we have several predictors, as I said, we can create a matrix scatter plot, kind of, determine or assess the relationship between each predictor variable with outcome variable. And this is how we can enter the variables into boxes in SPSS. We will have to check multiple boxes, and we can also run different plots to check for assumption testing, and we will get model summary. So here, this is model summary for multiple linear regression. We have model on the left side. There is a column called model. We have model 1 and model 2. So model 1 is simple linear regression, which means if we have only one predictor variable, our R will be 0.578 R squared adjusted R squared. If we have in model 2, we have multiple predictors. So we have different values for R squared, and adjusted R squared. So remember, if you see like model 1, model 2, that means we have either one predictor variable or multiple predictor variables. In coefficient table, this is our model parameters again. So we have model 1, model 2, and as you can see in model 1, we have constant, which is our intercept, and advertising budget as our predictor variable, as our single predictor variable. In model 2, we have constant, and we have three predictor variables. For each predictor variable, we will have beta coefficient. We have specific standard error for those beta coefficients. And we have standardized coefficients. And I will show you what's the difference between those. On standardized beta coefficients, we have units here. In standardized beta coefficients, we have units in standard deviations. And this is the assumption testing for multicollinearity. So based on the tolerance column and VIF, I would say there is no evidence of problematic multicollinearity among the predictors. Tolerance values range from 0.959 to 0.986. Remember, we don't have to look at number one because this is simple linear regression, and multicollinearity is not applicable here for simple linear regression. So we have to look at the column number 2, 3, 4, which indicates multiple linear regression model. So that's why the tolerance ranges from 0.959 to 0.986. So don't look at this one because this is for simple linear regression. And the VIF uh, are within the acceptable limits. These are, close to one. So there is no evidence of any issues for multicollinearity. So how can we interpret these models? So beta values, the beta values represents the change in the outcome associated with a unit change in the predictor. The standardized p-values. Remember, we say unstandardized beta coefficients or standardized b coefficients. So that's the difference. So we don't say standardized beta. We just say beta for unstandardized beta coefficients. So we have unstandardized beta values, which indicates the change in the outcome associated with a unit change in the predictor. But standardized p-values tell us the same but expressed as standard deviations. So for example, for beta values, the advertising budget, the beta coefficient for advertising budget was beta equals 0.085, which is here in this table. You can find 0.085. That is the beta coefficient for advertising budget in the second model or in multiple linear regression. So how can we interpret this number, this value? We will say because this is a when we look at beta coefficients, we also look at the sign of the beta coefficient, whether it is plus or minus. So this is plus. So I would say as advertising budget increases, I don't say decreases because there is no minus here. There's no the sign of minus. This is plus. So I would say increases. As advertising budget increases by 1 unit, album sales, which is my outcome variable, increases by 0.085 units. This is how I interpret the beta values, the beta coefficients. So both variables were measured in thousands. Therefore, for every 100,000 pounds more spent on advertising and an extra 0.085, thousands albums are sold. This interpretation is true only if the effects of band image and airplay are held constant. The second beta coefficient is airplay, which is here. It's the number of plays on radio. The beta coefficient is 3.367, 3.667. So I would say I would interpret this number as the number of plays on radio in the week before release increases by 1 unit. Album sales increases by 3.367 units. The image of the band, the beta coefficient was 11.086. So I would interpret this number as if a band can increase their image rating by 1 unit, they can expect additional album sales of 11.086 units. However, these are beta coefficients, unstandardized beta coefficients. If I want to interpret the standardized p-values, I would say so these values are 0.511. So I would say as advertising budget increases by 1 standard deviation, album sales increases by 0.511 standard deviation. This is the main difference between the interpretation of beta coefficients and b values or beta values. So this is a collinearity diagnostic. Um, this is another kind of another way of checking for multi-collinearity issues. Here, I can look at the condition index, and also I can look at the different values in each row for my predictor variable. So look at look at the three columns on the left side of the table. The three columns at the end of the table on the left side, they indicate my predictor variables: advertising budget, number of plays on radio, and band image rating. And look at those values in rows. So what I have, I don't care about model one. Why? Because model one is simple linear regression. I just look at model two, the model two rows. So I have four rows. If you see high values next to next, then I would assume that there is a collinearity issue. So here, I don't see, I have 0.96 for advertising budget, but the other values for number of plays on radio and band image rating are very low. So there is no collinearity issues there. And I have 0.93 again, but the values of the two columns next to this number are very low as well. So there is no collinearity issue. In dimension 4, I only have one high value, 0.92, but the values for other variables are 0. So I would say there is no collinearity issue here. So I can say the collinearity diagnostics do not indicate serious multicollinearity. Although the largest condition index was 13.22, which may suggest a mild collinearity concern, the variance proportions for the predictors were not simultaneously large within the same dimension. Therefore, multicollinearity does not appear to be a major problem in this model. This is how we check for homoscedasticity. So we can plot, uh, outcome variable on predictor variable. And I just want to see a random cloud of points, no funnel shape, no specific pattern. Then I would assume that the homoscedasticity assumption is met. And this is the histograms and PP plots for normality of errors. So the histogram of standardized residuals kind of represents bell-shaped curve. So, and the PP plot shows the data points, the observed data points are close to the diagonal line. I mean, not observed data points. These are not data points, but these are residuals, and these are close to the diagonal line. So I would say the normality of errors assumption is met according to uh, these plots, these graphs. This is how we report linear regression in APA style. So we have two templates here. One is for simple linear regression, and another one is for multiple linear regression. So for simple linear regression, I would say simple linear regression analysis was conducted to evaluate the extent to which independent variable could predict outcome variable. Then I would like I would write some statements and phrases like this. And here I have numbers like number one, number two, number three, number four, five, six, seven, 8, 9, 10, 11, 12, and 13. How can I get these numbers from these tables in SPSS? Then I need to plug these numbers into this template and it will be my simple linear regression. For multiple linear regression, it is going to be the same template, but it will be more kind of extension of this template because for multiple linear regression, I have to report the values for each predictor variable instead of just having one predictor variable. For your assignment, you will use the data file called module 6 in Blackboard, and you will have two linear regressions and one multiple regression. This means you have three research questions. For the first part of the assignment, you need to use total cholesterol and systolic blood pressure at baseline. And this is two separate analyses since we are not doing multiple regression. And here, the goal is to predict to predict BMI at baseline based on total cholesterol at baseline and systolic blood pressure at baseline. So these are two separate regression, simple linear regression analysis. Uh, the outcome variable here or dependent variable here is BMI at baseline. The independent variable or the predictor variable here is total cholesterol at baseline for one model. For the second model, the outcome variable is BMI at baseline, and the predictor or independent variable is systolic blood pressure at baseline. Always, always, always test for assumptions first. So for this one, the first part of your assignment, you have to make a scatter plot to see if there is any linear relationship between two variables, and then check for homoscedasticity, normality of residuals, um, independence of errors, um, any outlier or influential cases, all those things. And then you will need to run appropriate analysis and plots. You will have to write the results and then make conclusions about findings. For the second part of the assignment, you will have to run one multiple linear regression to find out to what degree baseline food frequency. You need to create a variable called FFQ at baseline or FFQ underscore 0 using the variables calcium, dairy, fiber, fruits and veggies, and sugar. Household income and sedentary minutes can predict BMI at baseline. So for this assignment, you need to first create the variable called FFQ underscore 0 or food frequency at baseline. And then you will need to enter all those variables into the model and run the regression. But you have to check for assumptions here again. You need to check for multicollinearity because we have multiple predictors. And then using the template, you need to report the analysis. So for regression analysis, the research questions can be like, to what extent does independent variable predict outcome variable? Or we can phrase it as, is there a significant relationship between X and Y? These are two different uh, ways for um, f- phrasing regression questions. This is an example of results section. So in your results section in the assignment, I would like to see different headings for your assumption testing. So you will have a heading for linearity, normality, independence, and homogeneity of variance or homoscedasticity. And then you will have to report your main regression analysis in your results section. Remember, just like previous assignments, you have to have a table for like demographic characteristics at the beginning of the results section. So I'm gonna stop here and I'm gonna show you how to run regression analysis uh, in SPSS. So this is the data file you will have to use for assignment uh, for module 6. So as I said, you will have to run two simple linear regression and one multiple linear regression. For the multiple linear regression, you have to have a new variable called FFQ at baseline. So how can I do that? How can you create that variable? So if you go to the to transform compute variable, I'm gonna reset this. And then target variable is your new variable. So you need to name your new variable here. So I just name it ffq underscore 0. And then for this numeric expression, I have to open a parenthesis. Depending on your variable, you don't have to have parentheses always, but I will show you why I need a parenthesis here. So I need calcium at baseline plus dairy. Oops, sorry. Dairy plus fiber plus fruits and veggie. And then I need to close the parentheses and then minus sugar and then click OK. Click OK. So this will create a new variable. So if you go to the variable view, scroll down, you will find FFQ here, which is a scale, and I just created this. So for the regression, I'm gonna go back to the data view. For regression, I would go to Analyze, Regression, and Linear. So for example, I have dependent variable as systolic blood pressure at baseline and my independent variables or my predictors variables are calcium and fiber. And if you look at this method section, this says enter. So if I just click on enter, this will be a forced entry method. But I can just change it. I can use stepwise, remove backward, forward. There are different methods. So, um, but I just leave it as enter because I want my predictor variables to be entered into the model simultaneously. So after you entered your dependent variable or outcome variable and independent variables to this block, um, you have to go and check for different options here. and I will show you that. But uh, let me ask you a couple of questions. So this will be a multiple linear regression because we have one outcome variable and two predictor variables or two predictors. So this is a multiple linear regression. On the other hand, my research question would be, is there a significant relationship between systolic blood pressure at baseline and calcium intake and fiber intake at baseline? This can be a research question for multiple linear regression. And here I want to predict systolic blood pressure by looking at dietary calcium and fiber intake. So let's go and check for statistics. So click on statistics. I hope you can see this table. So you need to check for estimates, confidence intervals, and then put it as 95. Check model fit, R squared change, descriptives, part and partial correlations, and collinearity diagnostics. And then for the residuals, check for Durbin-Watson box and case-wise diagnostics. So outliers outside two standard deviations. And then click continue. Let's check plots. So in the plots, for the y variable, enter ZRESID for y, and for the x, enter ZPRED. And then check for histogram, normal probability plot, and produce all partial plots. And then click continue. Then click on save and check for unstandardized, standardized, adjusted in the predicted values section. For distances, I just want to uncheck, I just want to leave Cook's distance here. And then for residuals, check for standardized, um, deleted, student, studentized, deleted. For influence statistics, check for standardized um, and covariance ratios, and then click OK. For options, there's nothing here. For style, there's nothing, and bootstrap, there's nothing, and then click OK. So this will be my regression output. So I have descriptive statistics indicating the mean and standard deviation and the sample size for my outcome variable and predictor variables. I have a correlation box. So instead of using a scatter plot, I can just check the correlations. But it would be better before running the regression. I It would be better if I would go to the graphs and then chart builder. I'm gonna reset this. So chart builder and then choose from scatter. You can choose simple scatter plot or matrix. So I would choose matrix and I would enter my outcome variable, which is systolic blood pressure at baseline, and then calcium and fiber, and then click OK. And this will create a scatter plot like this. So I can see if there is any relationship between two variables. So I can look at this scatter plot uh, by creating a matrix scatter plot or a simple scatter plot. So if I go back to chart builder and then reset it, click on simple scatter plot, and then I would enter my outcome variable or y to y-axis, which is my systolic blood pressure at baseline and calcium. So here, as you can see, I would say there is no relationship because there is no line. And if you double click on it, there will be a new window pop up and you can click on this graph, I mean this option, and then check the linear, and then mean apply. So oops. So as I can see, actually there is no relationship between calcium intake and systolic blood pressure at baseline. Um, oops. Okay. And then I will create another um graph, another scatter plot for my other predictor variable, which is fiber at baseline, and then click OK. And again, here I don't see any like a straight line pattern for fiber and systolic blood pressure. So I can do that, or I can just look at this correlation box, and I can see here significance. There is a correlation between calcium and fiber, but there is no correlation between calcium and systolic blood pressure. And also, there is no correlation between systolic blood pressure and fiber. So there is no correlation. There is no linearity here. So the assumption is not met. But let's assume that there's a correlation, and let's move on. So this is the model summary. I have just only one model, so I don't have any simple linear regression. I just have multiple linear regression, so I have just one model. I don't have two models. And I have R squared and adjusted R squared. And as you can see, these values are very small. These are very small, and I can say, and the significance level is it's not significant. It's not less than 0.05. So overall, the model is not significant in this case. And the Durbin-Watson value is 1.872. The Durbin-Watson value shows the independence of errors, and the value around 2 is okay, it's good. So the assumption for independence of error is met here. Um, the ANOVA table, this one shows the F statistic and the significance, the p-value for that F statistic, and the p-value is not less than 0.02, 0.05, sorry. So it's not less than 0.05, and it is not significant. So again, the model uh, is not significant, which means I cannot predict systolic blood pressure using calcium and fiber intake, dietary calcium and fiber intake. The coefficients table, I have constant, which is my B0 or intercept. So this is 124.83. This number means if calcium intake and fiber intake both are 0, my systolic blood pressure at baseline is 100 to 124.83. That's uh the concept of constant or intercept. The beta coefficient. If I look at the unstandardized beta coefficient, this is the for calcium it is 0.005 and minus 0.318 for fiber. Look at the significance column. None of them are significant. But let's assume these are significant. Just for this example. How can I interpret this unstandardized beta value? So I would say every unit increase, or I would say as dietary calcium intake increases by 1 unit, systolic blood pressure at baseline increases by 0.005 unit. How can I interpret this beta coefficient for fiber? And remember, the sign is very important. This is minus. I would say as dietary fiber intake increases by 1 unit, systolic blood pressure decreases by 0.318 unit. This is how I can interpret this. And I have standardized coefficients for beta, and I have correlations table. I have collinearity statistics. So I have tolerance and VIF. The tolerance should be more than 0.2. So this is okay. The VIF should be less than 10, and we are okay. So I would say the multicollinearity, there is no evidence of problematic multicollinearity. In other terms, calcium and fiber intake are not correlated with each other. I can use this one, or I can use this collinearity diagnostic table. I just want to skip that. Um, I want to skip this case-wise diagnostics here because we will use this one. So this is histogram for systolic blood pressure. Based on this, I would say this is the histogram for um, normality of errors. Based on this, I would say the assumption for normality of errors is met for systolic blood pressure because this is kind of a bell-shaped curve. And this one, the points are kind of close to the diagonal line. So I would assume the normality of errors are met. This is the standardized predicted value and standardized residual. I don't see any pattern here. I just see a random, pattern of points, data points. So here also, I would assume that um, the assumption for um, both like homoscedasticity and homogeneous variance are met here for overall. Um, Let me show you the outliers and the influential cases. So if you look at this residuals statistics table, you would find Cook's distance And the Cook's distance, the minimum is 0 and the maximum is 0.102. So any case, the Cook's distance, the absolute values should be greater than 1. If the Cook's distance is greater than 1, there will be a concern for outliers. So I don't have any outlier here because the Cook's distance is way less than 3. Or I can also look at the let's see, absolute value for standardized residual. It is here. If it is 3 or more, then I would have, there's a likely to have an outlier. But since the Cook's distance is not greater than 1, I would assume that there is no um there's no concern for outlier. So this is the output, and you need to report this in your assignment in the appendix section. I'm gonna share my screen again. So let's move on. And you can just look at this. I just showed you, I just here, I also added dairy here, but I just removed when I was doing the analysis, just keep that in mind. So, so make sure you check all these boxes when you're doing, and this is the output I have put here. And this is kind of how to report. So I would say in the results section, you would say prior to conducting the multiple regression analysis, assumptions were evaluated, visual inspection of the histogram and normal PP plot of standardized residuals indicated that the residuals were approximately normally distributed. Examination of the scatter plot of standardized residuals versus standardized predicted values suggested that the assumption of homoscedasticity or homogeneous subvariance was met. The Durbin-Watson statistic was X, indicating independence of errors. Multicollinearity diagnostics suggested a moderate concern, particularly for calcium and dairy intake, which were strongly correlated. The tolerance values range from blah blah, and the inflation factor VIF values range from blah blah. So you need to report these. Although a few potential outliers were identified based on the standardized and studentized residuals, Cook's distance the values indicated that no case had an undue influence on the model. This is how you will kind of report the assumption testing, but I would like you to have different headings for each assumption testing in your site.